we can start. So first of all, can you all hear me well? Because my voice tends to be low and go even lower. So if at some point you can't hear me anymore, just wave at me and say, please, raise your voice. So we already know each other. I'm Nicolò. I work here at CSS Foundation. My main field of research is modeling epidemics. So today I will give you a lecture on this, on the basics of how mathematical modeling of epidemics and computational modeling of epidemics works. And I also hope to give you an idea of why this is important, also outside of specific examples such as infectious diseases, but for example also in social sciences this topic is important and matters. So today we talk about epidemics. The most common example are infectious diseases, and COVID-19 is the clearest example I can give you of an epidemic. But the point is that actually this kind of dynamics can be found in many other sectors. So do you have any idea of other example of epidemics? Something related to your research? Yeah, epidemics. So an epidemic of information.
Emotions.
Sorry?
Emotions.
Emotions, exactly. So also in the case of emotion, you can have an epidemic of happiness, of anger, whatever. So we have emotion, we have informations. If you think also about ideas, innovations, or we have memes. I was looking at you because you didn't say you would have landed so well. I said, okay, it's about saying memes. Okay. Memes, so content on the internet. I mean, not by chance that we say that things go viral, because they behave like viruses. Yeah, it's quite important.
Yes.
No problem, but
سنمس بشو كابوت الدرس.
otherwise we can close the window. So memes, so content on the internet. Ideas, we already mentioned this. Misinformation, this is something that we mentioned at the beginning. The point is that, in my opinion, all these different phenomena, they all share some very fundamental ingredients, and this is why across very different settings we observe the same dynamics. And the three fundamental ingredients of epidemics are, first of all, individuals. We can call them individual, susceptible, agent. So these are the first fundamental ingredient. So the second fundamental ingredient is that we need something that spreads through the population, through the individuals. So it can be a virus, it can be a bacteria, any kind of pathogen, but it can be an idea, it can be an emotion, it can be an information. And the third fundamental ingredient are interactions. So if something has to spread, there needs to be interaction among the individuals through which this something can spread. So you already see that these complex phenomena can be somehow divided into very simple elements that by interacting with each other, they create the complexity of epidemics. And so the point is that every time you have these three ingredients, you have an epidemic. And this is why this pattern is common to many different settings. So, if you are a complex system scientist, you heard a lot about epidemics, and I mean, many people are interested in this. And why? Well, I think that the reason is that epidemics are a perfect example, like textbook example of complex system. So, because they, as we will see, they show phase transitions, the presence of tipping points. What is a phase transition? So you have a system, and the system behaves in a certain way, and for specific combination of parameters, so in very specific conditions, the behavior of the system completely changes. So this is called phase transition. and it's a common feature of complex systems. And the tipping point is the point in which this change of behavior happens. There are emerging phenomena within the context of epidemics, also feedback between spread and behavior, between the spread and the individuals. This was obvious in the case of COVID-19. For example, the spread of the virus was not independent from the behavior of the people, and the behavior of the people was not independent from the spread of the virus. So people reacted to the spread, and of course they influenced the spread, and the change of the spread influenced back the behavior. But this can also be true for other settings, such as the spread of content online. So the people, the behavior of the people influence the spread, and is influenced back the behavior of the people. And after all, they are relatively simple processes, because as we have seen, you have 3 simple ingredients, and you have an epidemic. But the outcomes can be complex. And second question is why computational social scientists should care about epidemics. So why we are here talking about epidemics in a computational social science summer school. So think again at the 3 ingredients: individuals, something to spread, and interaction. And at least out of 2 out of these 3 ingredients has something to do with social science, no? So individuals are not equal. So we, as a first instance, you can assume that in your population everyone is equal, but this is not the case. So, for example, in the case of COVID-19, we have seen that some people were more prone to get the disease because of their occupation, so on and so forth. But this is the same, for example, in online platforms. So not all people are equal in an online platform. People will be more inclined to believe to certain ideas than others, for sure. And the interaction. So the interaction are also very heterogeneous. There is an entire field that studies how people, humans interact, and network science comes into play a lot into this. And we will somehow get to this later. Okay, so this was the introduction, let's say the motivating examples on why we should study this phenomena and why I think they are interesting phenomena. And now we will go to the actual modeling of this phenomena from a mathematical standpoint. And by the way, I didn't mention this, but if there are questions, comments, whatever, just interrupt me at any point in time. And are there any questions and comments on this first part? Okay. So let's go to let's try to answer to this question. So we have this system. How do we model this system from a mathematical point of view? So the base to all the mathematical modeling of epidemics are compartmental models. A compartment in this setting is nothing but a group of individuals that share some common feature. So this is the most simple example of an epidemic that you can think of, and it's called the SI model. So these compartmental models are named after the compartments. So you can see that the SI model is named like that because there is a group of S people and a group of I people. So the S people are the susceptible. So these are the individuals, the agents, the first ingredients of the epidemics. And they can get the disease. The second group are the infectious individuals. So these are individuals that were infected in the past and are now infectious. So they can pass on whatever they are spreading to the susceptible. And how this transition happens? Through the interaction. So anytime a susceptible individual interacts with an infectious individual, the susceptible individual can become infectious with a certain probability that we call eta. This is the most simple example that you can think of. And it's a compartmental model. So in general, compartmental models are represented with very simple scheme, graphical scheme, that tells you what are the compartments, so what are the groups, and what are the possible transitions. So here we have 2 groups, Si and 1 single transition, from S to I. That happens through the interaction between S and I with a probability beta. As I said, this is a compartmental model. You have seen that in compartmental models, individuals are divided into compartments, which are another name for groups. And individuals are grouped according to their health status. So here I'm putting health in parentheses, because as we will see, to extend this framework, we will have to think at compartment not just in terms of health. I'm infectious, I'm susceptible, I'm vaccinated, but this can be used to represent also behavior. So I am more susceptible than someone else. I am a super spreader, whatever, something like that. And we have seen that we have transitions, and the transition among compartments happens at given rates. So before I used the word probability for the sake of simplicity. Beta is actually a transition rate, and we'll see what is the difference. It's not super important at the moment. An important point is that transitions, so the movement of people from one compartment to another, can be divided into two main categories. So the first category is infection processes. So an infection process, as the word says, is mediated by an infectious agent. So if we go back to this example, this transition is an infection process because the susceptible, they interact with the infectious and they become infectious themselves. But we have other transitions which are spontaneous. So individuals change their compartment without any interaction with other compartments. So think, for example, at the recovery process. So you are infectious, unfortunately you got the flu, but after a while you will recover. You will not be infectious anymore. And this happens spontaneously. It's not that if you have a lot of healthy people around you, you recover faster. Okay, but this is the model that we have just seen. It can be extended very, very easily into other models. These are very, very famous. The SI model, we have just seen it. This is basically used to model cases where infection is permanent. So a susceptible, become infectious, and remain infectious. So if you simulate this in a population, in a closed population, eventually everyone will become infectious at some point. Another very famous example is the SIR model, and this is generally will be our main example today. And in an SIR model, infection is not permanent. So you see that the first part on the left-hand side is equal to the SI model. So it's susceptible, interact with infectious, they become infectious themselves. But then we have an additional transition, which is the recovery process. So with a probability mu, with a rate mu, it's better to say, the infectious can recover. So they move to a compartment, R, which stands for recover, remove, depends on the textbook. And they are just there, they can't infect anyone, they can't get infected, they have immunity, and they are just there. And here we are assuming that immunity is permanent. This is not always the case. For example, we have, in the case of COVID, immunity after some time fades. But I mean, generally, we are interested in time scales that are relatively short, so we can safely assume that most of the time the immunity is permanent. And then we have a third model, which is the SIS model, which is similar to the SIR model because also here we have a recovery process. So infectious, they go out from the infectious compartment at some point with a certain probability, but they go back to the susceptible compartment. So this means that there is no immunity. You get infected, you recover, but you can get infected again. And the only difference with the this SI model is that while here at some point everyone will become infectious, in the SS model it can be shown that you reach a steady state in which there is a perfect balance between the people that get infected and the people that recover from the infectious. So you will have a constant number of individuals who are infected, which is less than the total number of the population. And that you can take a very simple framework and you can extend it, adding compartments, adding transitions. Sorry, there is a question.
So I just want to ask if in a system we have more than two models, for instance, different about the other, for instance, they can get the infection and then, you know, there can be different ways of adopting SIR and SSS model.
No, it's, these are very good comment. The answer is yes. So we will get to this somehow. But the point is that you can create a compartment which, let's make this example. There are someone that get immunity and someone that doesn't get immunity for some reason. So you just divide the population, you create two compartments, S1 and S2. S1 are the people that can acquire the immunity, and S2 are the people that for some reason do not acquire the immunity. And you model them in the same way, but the S1 will end up in the R compartment, and S2 they will end up in the S compartment after infection. So the point here is that these, of course, are the most famous models. There are reasons why these are famous, because you can model a lot of things, but depending on your problem, you can take this framework, add compartments, add transitions, and more or less things works the same. And you can use a very, very similar tool to analyze the system that you are building. And we will see how to actually analyze this, and if the compartments and the transition change slightly, the analysis don't completely change. But the nice part is that, what I was saying before, these are simple systems, relatively simple stuff, from which complexity emerges. And we will see that. And I mean, it's quite surprising to me that a very simple process like the SIR model shows a phase transition, and we will get to this. Okay. Okay, so now we go into the mathematical part. So I will try to be very light on mathematics. I don't want to bore you with after lunch. We have a coffee break later, so I mean, let's try to be very relaxed. The point is that you can take these diagrams and turn them into a system of differential equations. So the SIR model there, and these things are the very same thing. You just have to understand how to read this diagram and turn it into this thing. Question?
Sorry, what is Sagan equation?
This one, this thing here?
Yeah.
Okay, we'll get to that. We'll get to that. Yeah. This is actually a very, I mean, you spotted something strange, because in the SIR model, in general, there is no C. But here I wanted to factor take out this factor, and I hope that I will manage to tell you why in a clear way. But we'll get to that. So, first of all, what is a system of differential equations? So, a system of differential equations is this thing. And a differential equation is nothing but an equation that tells you how this quantity evolves in time. So this is the number of us as individuals, so the number of susceptible individuals. And this expression tells you how the number of susceptible change in time. We will analyze this expression, but just notice there is a minus. So this is telling you that the process, the number of susceptible decreases. And the reason is that people becomes infected, and it is no surprise. This is the number of infected people, how change in time. Well, you have first you have a positive contribution, which comes from the fact that people becomes infected, and then you have a negative contribution, which comes from the fact that people recover. And finally, you have the number of recovered only increase in time because people recover. So, if we look at the diagram over there, we have two transitions, infection and recovery. And here they are. So this is the infection term, and this is the recovery term. So you just plug these blocks into this system of equations. So the number of susceptible diminishes in time because people get infected. The number of infected in time, on one side it increases, and on the other side it decreases, and the number of recovered just can increase. Don't look at the specific beta C, we'll get to that, but I just want to familiarize with this notation. Is this somewhat clear? If it is not clear, just raise your hand and I will try to explain better. I assume this is quite clear. Why we are going through this pain? Because this is a mathematical object, and you can apply mathematics to get to understand the behavior of the system, basically. There is also a note that we have to make, and here we are assuming that the number of people in different compartments, SIR, are continuous quantity. But this is, of course, an approximation because you can't have half people infected. So these are discrete numbers, but differential equations works for continuous function. So we are assuming somehow that they are continuous. And if you consider very big numbers, I mean, saying 100,000 acceptable and 100,000.3 acceptable doesn't really make a big change. Okay, so now we will try to understand the infection term. So the question is, what are the factors influencing the force of infection? The force of infection is nothing but the probability of getting infected. You are a susceptible individual, and there is a certain probability that you will become infected. And the mathematical expression of this probability will depend on some factor. So you have already seen it, but we didn't comment it. So the question is, if you have to guess, what are some possible factors that influence the probability of getting infected?
Frequency of interactions.
Exactly. This is certainly one point. So the frequency of the interaction is a good point. Another one?
Level of susceptibility.
This is a very, very good point. The level of susceptibility. Absolutely.
And the peers.
Sorry?
The peers.
So who is you are in contact with? Yeah. This is another point.
Nature of the interaction.
The nature of?
The nature of the interaction, not only the frequency.
Absolutely. For certain diseases spread only through certain interaction. Absolutely. Any other? Even more trivial.
Number of people who are already infected.
Exactly. The number of people infected. So if no one is infected, there is no spread. And I would add also some characteristic of the virus, of the things spreading, so that what is spreading will have some intrinsic transmissibility. So this is what you said. So for sure, this probability of infection will depend on the number of infected people. Because if no one is infected, this probability has to be. So the first factor is this I over n. So this is the number of infected people, and this is the total number of people. So this is the probability of meeting an infected individual. So if you have I people infected out of n, if you draw a random people, you will have a I over n probability that this person will be infected. The second factor is this C that was mentioned before, and we said that the frequency of the interaction. So for sure, the number of contacts an individual on average has will influence the probability of infection. So we have a problem. What is the probability of finding an infected people, and what is the number of contacts we have? And then we have beta, which is the probability of a single contact. So each contact C will have a probability beta of leading to an infection, and this is the probability of finding an infected people in a population of N. We are leaving a lot of things out, because someone mentioned the nature of the interaction. We are not considering this here, because this is a very simple framework. We are leaving out the fact that people may have different kind of contacts and different number of contacts. Here we are just saying we are considering an average guy that has C number of contacts. We will try to extend this in the end. Basically, the main limitation here is that we are assuming homogeneous mixing. So this is the main limitation of compartmental models, as we are explaining them. What this means? So the homogeneous mixing assumption assumes that people are like particles of a gas bumping into each other, moving completely random. This is not really the case, because I mean our society is not a gas and we are not particles. But as a first as a first approximation, it works relatively well. And the point is that also these assumptions simplify a lot of the problems and allows us to derive a lot of nice properties, a lot of nice results. But by the end of this, we will try to relax this assumption. So the point is that by simply guessing and making some assumption, we derived the probability of getting infected, assuming that everyone is equal and assuming that everyone has the same number of contacts and assuming there are I individual infections. And let me go back a second, and this is exactly this term. So the number of susceptible individuals in time will decrease, and this, the number of people that will be basically infected in the next time step are this probability that we just derived times the number of susceptible. So assume there are 100 susceptible, you compute this term, which is, I don't know, 0.3, and so the number of people who will get infected in that time step will be 0.3 times 100. So
we were assuming that C and N are not a function of T, right? Because
exactly.
Infectious people are staying in the community.
Exactly. This is a very good comment. We are assuming that N is constant, so the number of people doesn't change. So no births, no one dies, no one is removed, no one is quarantined, no one is isolated. And we are also assuming that C is constant. So the number of contacts is the same every day under every condition. And this is also, you already start to see this limiting assumption, because the number of contacts shows, for example, some seasonality patterns. Assume your typical week. On a work day or on a weekend day, you will have different number of contacts, I assume. And also, if you are within a pandemic, your contacts will change over time, either because you, at some point, you stay at home, or because at some point the government says, we are closing down schools, we are closing down workplaces, non-essential shops, etc.
So is this like the R naught that the epidemiologists use, like initial reproduction number?
This is a very close relative of the R naught, and we will actually derive R naught mathematically. But you already start to see where we are going, exactly. Okay, so I hope you are convinced that this thing here can be translated into a mathematical object, and that we have provided reasonable arguments that these terms make sense under certain assumptions and limitations. Now, I mean, don't get confused, but I wanted to take C and put it there, because actually the number of contacts is an important factor. But if you open a textbook about SIR model, this term will simply be beta times E divided by N, because these two guys always happen as a product. So it doesn't matter to have beta times C or just a single factor that we call beta. So most of the times C is encoded into a single beta. So you don't see beta C E divided by N, you simply see beta. So in the following, to avoid the redundancy, we will just say beta, but it means beta times C. And now we will try to derive the R naught, the R0. So what is the expression of R0? And for those of you who doesn't know, R0 is basically a measure of how bad an epidemic is going to be. But we will see what is mathematically, and also we will interpret R0. So now take this equation. So this is the equation that describes the evolution of the number of infectious people in time. It was in the system before. We have just take the second equation on the number of infectious people, and we brought it there. And now we will solve this equation under a certain assumption, which is called the early stage assumption. Early stage assumption means that we are at the very beginning of the epidemic. So at the very beginning, if you think about it, the number of susceptible will be big. So there will be very, very few infected people in a population. So the point is that at the beginning we can safely assume that the number of susceptible will be equal to n, approximately equal to n, because no one is recovered and mostly no one is infected. As, take Italy as a country, we are around 60 million people. February 2020, probably there were few thousands of infected by COVID-19. So we are talking a tiny fraction. So we can say that everyone is susceptible. So this has become n. So you see that we can simplify n with n, and the equation becomes that how the infectious people change in time is beta it minus mu it. So you can simply write this as beta minus mu times it. So you have one more step, and this is simply algebra. So for some reason we are taking mu out of this parenthesis, and so the parenthesis becomes beta mu minus 1. So this is just, we are deciding to do that. And we are deciding that beta divided by mu, we call it R0, R0. And this is the final equation. So you have the derivative of a function is equal to some coefficient times the same function. And anyone want to guess which function has a derivative which is equal to the same function plus times a coefficient? And this is an exponential. So because if you take the derivative of an exponential, you simply get again the exponential times the exponent. So this is the solution.
There's a t missing in the exponent, right?
Good point. Here. Because otherwise it would be 0. Yeah, there is a missing t here. This is a very good observation. But this is the how the number of infected, this is the exact solution of this equation under the assumption that S is mostly equal to n. And we have seen that now appears this R0 guy, and we will see what is the interpretation of R0. Okay, if you open a textbook or a Wikipedia, this is the definition of R0. So R0 is the number of secondary infections that are generated by an infected case in a fully susceptible population of infinite size. Okay, so in practice, this is the rule. So if R0 is greater than 1, the epidemics will grow. If R0 is smaller than 1, the epidemics will fade away. Why? So think at the case of a population, and assume that in this, in general, in the population, to generate an offspring, you need 2 individuals. So if everyone has 2 children, you assume that the population under certain assumption will remain stable. If everyone has more than 2 children, the children will replace the parents and the population will grow. Otherwise, if everyone has 1 child, the 1 child can substitute the 2 parents and the population will decrease. And this is the very same. Here we have that an infectious individual, if the infectious generate on average less than another one infectious, then the epidemics will decrease because the new generation won't be able to substitute the previous generation. But if each infectious individual generates more than 1 new infected, the epidemic will grow because the new generation will substitute completely, and there will be also more than the previous generation. So this is a graph that shows you the previous function, plus the t that is missing, plotted with a logarithmic scale that shows you in time the evolution of I. The logarithmic scale is just for plotting purposes, so that this looks like straight lines. So you see that if R0 is equal to 1, the initial number of infected remains constant. If it is smaller than 1, it goes to 0. If it is greater than 1, it goes up.
I have a question about R0. Is there a unit? Is it the same unit as the epidemic? Like 1.5 is 1.5 people?
Okay,
or?
these are the
Okay.
So actually, R0 is a dimensional because it is a ratio between beta and mu. which have the same unit of measure, which is time to the -1. So it is high dimensional, but the interpretation is the number of people that will get infected by a single infection. So you can think of it as people. So yes, 1.5 means that I infect this, I will infect 1.5 people. This is the exact definition. And if you look at it also at the definition, beta is the speed at which infectious reproduce themselves. Because there is the probability of infection of a single contact, while mu is the rate at which infectious recover. So if the infectious are faster infecting than the recovery process, then we will have an epidemic. Otherwise, it will go away. So there are many, many ways of looking at it. But this is interpretation. And this is the phase transition that I was mentioning at the beginning. So you have a system, R0 equal to 0.5, you have a behavior, 0.6, you have a very similar behavior, 0.7, very similar behavior, you go, and then when it is 1.1, you have an epidemic, you have an exponential growth. Okay. If you plot the function that we just derived, this is what you get. And you understand why in the previous slide I was using a logarithmic scale, because these things grows very, very, very fast. And the point is that if you keep plotting, these things grows forever. I mean, there is no reason, if you look at this function here, there is no, this is a always increasing function. The point is that, it's over there. And the t is still missing out. So if you think about it, this is impossible. So at some point, the epidemic will peak. I mean, there is no infinite number of people to infect. So indeed, this is an assumption, it's an approximation. So we are, if you remember, we derived that equation under the assumption that the number of susceptible is more or less the number of people. But at some point, this assumption will break. And indeed, it breaks, because if you actually plot the number of infected, you see that it is something like that. So this is a typical shape of an infection curve. So it grows, at some point it peaks, and then it goes down. And you see that at the beginning, it follows quite nicely the exponential growth, but then at some point the two curves completely diverge. And so the point is that the assumption we made is good just when t is very small, just at the very beginning of the epidemic. And so R0 makes sense only when you are in that region. Because someone mentioned at the beginning that the probability of getting infected will depend on the susceptibility. This is true. And R0 will be the number that I will infect only when the population is fully susceptible. Because suppose that you have a disease with an R0 of 2. But if everyone is immune, then the actual R0, the actual reproduction number will be 0. No one will get infected. And this is why there is another quantity which is called R, which is a sort of dynamic version of R0 that also takes into account the fact that the susceptible population decreases over time. So the chances of infecting someone becomes smaller and smaller. So it becomes very difficult to find someone who is susceptible. And this is a classic plot of an SIR model in which we integrate the equations, and we will see how to do that. And this is the typical shape we have. So we have the number of infectives, we peak at some point, then it goes down, the number of susceptible decreases, and then at certain point it plateaus, and the number of recovered increases, and then reaches a plateau. Actually, you can derive an analytical expression of that plateau, and it depends on R0. Is a question? Okay, so this is, I hope, clear, but it's also very, very simple. And question.
Sorry. So the number of susceptible decreases. That's why the spread slows down.
Yes.
But on the other hand, the number of infected increases at the same time. So that more people are infected compared to the beginning. So how do we account for that already at the beginning that we are not?
Can you say this?
So when you asked in the beginning what determines the speed of the infection, and one of the answers was the number of infected.
Yes.
So the more people you have who infect other people, the faster it will spread.
Yes.
And here we see that we said that the number of susceptibles determines that. As the number of susceptibles decreases, the spread will decrease, but number of infected is increasing at the same time.
It's both. So it's a combination of the two factors. So the more infectious you have, the higher the probability. But the lower is the number of susceptible, the lower is the probability. So you have these two factors that
countervailing.
Yeah, exactly. Because when the number of infectious grows, the number of susceptible goes down. So you have two forces going into different directions, but at some point they balance, and this thing goes to 0, and this thing goes to a certain amount. Okay, so this is a very simple framework that can be extended as you wish, basically. So, for example, in the case of COVID-19, I mentioned a lot of COVID-19 because this is a very vivid example, and my research in the last couple of years were dedicated to that. So, for example, an SIR model was not enough to model something like COVID. Why? Because you have a lot of other health status. So you have individuals who are vaccinated, you have individuals who are asymptomatic, you have people who are pre-symptomatic, you have people who are hospitalized, so on and so forth. So this is why in our research we took the SIR model and we extended it, adding compartments. So these things may look scary, I don't know, but this is the same as an SIR model with something more. So this is the susceptible, we have the infection, they do not become infected, they enter a latent stage in which they are just infected, but they can't infect the others. Then they enter a pre-symptomatic stage. When they are pre-symptomatic, they can either become infectious or they can either become asymptomatic. The asymptomatic at some point they recover. The infectious at some point they either recover or they die, unfortunately. And you see these all transitional, their own probabilities. So this is the same as before with more compartments, more groups, more transitions. But if you look at it carefully, the structure is the same. This is what we developed for multiple variants. So SARS-CoV-2 mutates a lot. So we have the alpha variant, the Omicron variant, the Delta variant, so on. And what you do, you simply split the infectious compartment. So you have the susceptible again, but we don't have just one compartment for the infectious, but we have two. The infectious with the variants and the infectious with the, we call it wild type. So it's the previous circulating strain. But this is again the same, because you have the infection process, the recovery, and so on. Then vaccination, again, what you do is simply add compartments. So these are the vaccinated with one dose of vaccine, these are the vaccinated with two doses of vaccine, but the structure is very similar. You have the susceptible, you have the infected, the infection process, the recovery, and the same for the vaccinated with a probability which is smaller, because they have some protection by the vaccine. So I don't want to get into the details and it makes you understand exactly what we did, but this is just to say that you take the simple framework, you extend it, you add the compartments that you want, you write down the system, and you have the book. More interesting for you. Compartments may represent behavioral classes. So it's not just infectious, latent, pre-symptomatic, asymptomatic, but you may have different individuals. They are more or less susceptible to a virus, for example, because they either engage in some sort of behavior change. For example, I wear a mask, or I have a certain level of education and I do not believe to this misinformation, or I was not exposed to some other information, some other ideas, therefore I do not believe to this, I do not spread this information. this is, again, related, this is what I said at the beginning, is that the point is that epidemic and behavior are completely intertwined. So you can't disentangle them completely. Because the epidemic, the fact that there is something that spread among the population will make the people to make their choice and change their behavior at some point, no? And again, the fact that people change behavior will affect the epidemic. So,
what happens when the epidemic is behavior? Like, it's a type of thing that's spreading around. Like, let's say, jewelry or like getting your ears pierced. That's a behavior that spreads through the community, but it's also, it's like, it's both sides of the feedback loop. How does that work?
Yeah, that's an interesting, that's an interesting comment. So I would say, here I call it epidemic and behavior, but this is mostly, it should be changing behavior. So, and this can be whatever it spreads. So in your example, it's a behavior that spreads. If people change their mind, this will be reflected in the epidemic and so on and so forth, so on and so forth.
Okay. Maybe the thing that changes is the culture around.
Lifestyle, like you just said, I think it's almost contaminating the other practices that you have or the other behaviors you have.
Yeah, think of it like, so you mentioned fashion, right? No, you mentioned.
Yeah, let's say fashion, yeah.
Yeah, I was trying to find an example on this that makes sense, but yeah, this is mostly about, let's call it the classic epidemics, like infectious diseases, and I think this is clear. But in your case, I will think about it more closely, and I will find an example. But this is a good comment.
Because the general definition of a need is just information that spreads through, so it doesn't have to be a specific thing, but even a behavior can become an
something
epidemic.
spread. Yeah, this is a good comment. Yeah, absolutely. And this is how you extend the framework that we have just seen to behavioral compartment. So this is one example, but one can think of 100 examples. And here the susceptible are divided into two categories. So these are the classic susceptible, and these are the susceptible with awareness. Let's call it like that. So what happens here? They both get infected at some point, but the probability that the susceptible with awareness will get infected is smaller, because there is it's not beta, it's R times beta, when R is smaller than 1. So beta is greater than this thing. And we have an additional transition in which susceptible becomes aware when the number of infection grows. So this is the classic example when the infection grows, people start to get scared, and so they adopt some behavior change. So they get aware of the spreading, and therefore they adjust their behavior to protect themselves. But this transition, here I imagine it as mediated by the infectants. But it can be mediated by other things, like external factors, like news. You are exposed to some news, therefore you change your behavior. So this can be a function of, I don't know, the number of articles, the number of social media posts, whatever. And again, you take this diagram and you write it down as a system of differential equations, which is very similar to what we have seen. So we have one equation for each single compartment. Now there are 4, 1, 2, 3, 4, so 4 equations. We have the terms that we know, the infection, but we have an additional infection, which is similar to what you said. This is an infection of behavior. So the term is exactly the same, but what is spreading here is behavior, so the awareness, I call it. And again, we have the equation for the susceptible who are aware. They get infected at a lower rate, and the rest is more or less the same. This is again to say that what we have seen, you write down a system, you write down a model that fits your problem, you think about it a little bit, and you write it down as a system of equations.
In this case, the less susceptible ones are, if you're taking timers, linear timers, are afterwards, right? They were all susceptible at a certain level, but after some being infected due to the news or the awareness that is spread, they become less susceptible, or a priori there were people who were already less susceptible to their lifestyle.
Okay, okay. I see your point. So in this context here, everything is simultaneous. So assume that t equal to 0. Everyone is susceptible, they get infected. Okay. Time equal to 1. Some susceptible say, look, there is someone who is infected. Let's go into the awareness bucket. And then they will get infected. But you can also say, look, maybe there is already, this compartment is already populated at t equals 0 because we are not starting from scratch, but there is already someone in there. So at this time t equal to 0, this will be 0, would be 20%. And in that case, the R0 will be affected. Because if you assume that at the beginning no one is aware, R0 is the same. If you assume that at t equal to 0 someone will be aware, R0 will be a little bit smaller. And this is the plot. If you simulate the system, see that this is the curve when, let's say, when the aware people do not protect themselves effectively. When they start protecting themselves effectively, this curve goes down. So you are decreasing the number of infected. Okay, so I put this on another machine learning model. So what we introduced so far, they are called mechanistic model, and they are the counterpart of machine learning model, advanced statistical models. So in a mechanistic model, what you do is that you explicitly encode in your framework the physics of the problem you are studying. For example, here we are saying the probability of getting infected is beta times c times the fraction of infected, because this is something we know. In the case of a machine learning models, you don't do that. You ask the models to say, look, these are the data. What is the process behind? Can you tell me the physics of the process behind? So you give the models the capability to do that. There are pros and cons, and if you want, we can discuss eventually. But this is just to tell you that we are looking at a different class of model, which are mechanistic models. And the main pro of a mechanistic model is that it's easy to run counterfactors. So you assume that you have the model that we have just seen together, and someone comes at you and says, look, can you do a simulation where R0 is double? And you simply change a number and you run the simulation. If you have a machine learning model fitted on the data and you ask yourself, what would have happened if R0 was double? It's not easy how to implement it. So the point here is that when you know the physics, physics is a general word, when you know the mechanism behind the process, you should model this explicitly. Without using a machine learning. Okay. So any question? Okay, we have 30 minutes left, and I have a couple of sections to go. One is about technical aspects, and it is applied to what we have just seen, but it's a very general things that can be applied to other problems. So if how to implement these things. So you have seen the curves and all this stuff. So how do you do this with a computer language? And the other section will be extending this to include a social structure into the SIR model. So maybe I will go a little bit fast in the technical aspects because the code is on GitHub and you can give a look at it, but because I want to dedicate more time to the last part. Maybe the better idea is to look at the last section first and then dedicate time to the technical aspects if you don't mind. So don't look at it, don't spoil it. Okay. Okay. So the biggest assumption we made is homogeneousness. So we said people are gas particles, we put them in a box, we shake the box, and this is how people interact. Limitation. This is the spectrum, the complexity spectrum of epidemic modeling. But I think it can be applied to many many other settings. So we started from homogeneous space. So we are here. The next step, and we will look at it, is to add a social structure. So we have multiple layers of contacts. Then you can also model contacts as a network. Then you have multi-scale models in which you have also spatial layers. So you have cities, and people can move between cities, between countries, so on and so forth. And then you have the end of the spectrum. You have agent-based model. Each one is an agent. Each one is a key function. They have their own reasoning. A lot of you, I know, work with agent-based modeling, so you know much, much better than me about agent-based modeling. What is the trade-off here? Here, very simple assumption, lots of limitation, but easy. There, less assumption, very realistic, very difficult to implement. And it's lot of data, and it's, at some point, the model becomes so complex that when you want to apply it to the real life, it becomes tricky. So my experience is that when it comes to, my experience with COVID-19 is that we applied something, I would say here, and sometimes multi-scale models, but models that are not so complex. You would be probably surprised of how simple they are with respect to what we can actually derive theoretically. Another point that I want to make is that all these these other, how can I say, all these other models, more complex models, somehow they are based on this. So once this is clear, this is just about extending this. So take, for example, multi-scale models. They are generally called meta-population. A meta-population is nothing but a network of cities, a network of regions, and within each region we have the same. So you have again this or this. And people, you just add basically mobility flows, and people can move, but if we reduce at the single unit, it's the same of what we studied. So this is just to say that I think the difficult part is having this very clear, and then extending is relatively easy. And now we will dedicate some time to try to extend the SIR model to account for a social structure, which is a little bit more complex than the box shape. Okay, so now we consider a simple society with two groups of individuals. So we have A people and B people. And in general, in our society, we experience what is called homophilia. So people with similar characteristics, they tend to have contacts. They tend to mix together. In this context, a very convenient representation of contacts is through matrices. So this is a contact matrix that describes the number of contacts between different groups. So this term here is nothing but the number of contacts between A people and A people. This is the number of contacts between A and B, B and A, B and B. So this is the same C that we have seen before, but instead of being a number, is a matrix. So it's more dimensional, more complex. And this is what I just said. And I have a quiz. Question, is C symmetric? So this number here, the number of contacts between B and A, and the number of contacts, let me phrase this correctly. So the number of contacts that an individual of group A has on average with an individual of group B in a day is the same as the opposite? Or is not? This kind of question, the answer is always no. It's correct. But the first time I saw this, I said, okay, this has to be something similar, for some reason. And it wasn't symmetric, and so I started to think about it, and then I went to my supervisor and said, look, this is not symmetric. And he laughed, and he explained me why. And he explained me saying like this, so imagine you go to a dinner with Elon Musk, or maybe said Bill Gates. Someone mentioned Elon Musk. Let's pick Elon Musk. And you pay the same, but you pay the same bill, but he's taking this money from his bank account, you are taking this money from your bank account. So it works differently. And this is the same, because the number of people in A and B is different. So assume that between A and B there is 100 contacts, but in B there is 100 people, while in A there is 10 people. So on average, the R people will have 10 contacts, while in the B people will have just 1 contact. So this term will be 10, and this term will be 1, or the other way, I don't know. But this is just to say that this is not symmetric. Okay, so how do we extend the SIR model when C is not a number, but is a matrix? Well, it's not that difficult, because now this is the same that we have seen before, but the compartments now have a subscript, I. So this will be the number of susceptible people in the group I. Is the number of infected people in the group I, the number of recovered people in the group I. So you are just multiplying the compartments by the number of groups. Very simple. And what is the probability of infection now? So remember that we started from this. So beta times C, E divided by N. This was the probability of infection then. This is the probability of infection now. And let's try to understand what this is telling us. So beta is beta. So this is a property of the virus, of what is spreading. So it's the same. Then you have a summation over all the groups. So in our previous example, this will be a sum of 2 terms. And you will have here C, which is not a, which is an element of the matrix, so Cij, which multiplies Eij Nj. So first of all, consider this. So this is the fraction of infected individual in the group J, and this is the number of contacts that I people make with J people. So this is the same as before, but you iterate over all the J compartments. So the probability of infection for the I group will be beta times these things, which is nothing but a weighted sum of the fraction of infected in each group, weighted by how much contacts I people have with J people. So without, I mean, the mathematical details, you can look at it and eventually we can discuss, but this is not really different from before. This is just a little bit more complicated. And again, the system of equation, we won't have just 3 equations, but we will have 3 times k equation, where k is the number of groups. In the example I made, we have 2 groups, so we will have 6 equations, and so on and so forth. And this is the equation for us, A and R. And the probability of infection is the term that we have just seen. Fun fact, the R0, you can compute the R0 of this thing, and it still reminds of the old R0, which was beta divided by mu, and now the R0 is beta divided by mu times the spectral radius, which is the biggest eigenvalue of the contact matrix. Okay, an example. So a classic example where these things are used is when you segment people into age groups. There are many reasons why this is the case, and probably the first reason is that it's easy to measure contacts by age, because age is something somehow something objective, so you can measure objectively the age of someone, and also through surveys, just I ask you your age, your contacts, and you can build the contact matrix through age. And also because from an epidemiological perspective, age is generally a risk factor. So, for example, in the case of COVID, age was a risk factor. This is also the case for flu. So, having contacts layered by age is convenient. And another thing, probably more interesting for you, is that contacts tend to be very different across settings. And you know this much better than me. And these are real contact matrices from the UK, in which you see the, for example, the contacts at home. And this is what the contact matrix looks like as represented as an if-map. You see the diagonal. These are people having contacts with people of their age. So you have siblings here, partners, and then you have these 2 sub-diagonals, which are the contacts that children have with their parents in general. So intergenerational mixing. Workplace, you have these clouds in the middle. So at the workplace, you generally have contacts with people in working ages, spanning from 20 to 60. School layer, a lot of contacts are clustered here. People of age for school. other location is less clear. You still see the main diagonal. And this is C. This is, for example, we want to model the spread in a home at home. We take this matrix, this is C, we plug it into the SIR model. Yeah.
You get this contact data from other traditional data sources like survey. How do you measure?
Yeah, this is a good question. So, yes, there are surveys. But surveys are very costly to get. So basically, how these things are computed is that there is some ground truth data for some surveys, and then people build models and they compute synthetic contract matrices, saying, okay, let's assume that in the UK, the average household size is this number, the age distribution is this, the size of class is this, and they generate the contact matrix from this. So it's a mix of ground truth data and synthetic data generation. But these are available for all countries of the world, basically, in a mix of synthetic. If you are interested, there are some public repositories where you can download the contact matrix divided into these 4 layers for all countries of the world. And this is an example in which I implemented the SIR model with the extension of age. So people are divided into age groups. And I have applied it to population which is compatible with the United Kingdom and a population compatible with Kenya. So 2 very different settings in terms of context, but also in terms of age distribution. So you see that, for example, in Kenya you have a much younger population with respect to UK. And if you assume very same disease, very same initial condition, you get 2 different outbreaks. So this is the, again, S, I, and R for United Kingdom and Kenya. And you see that they are very different, but this is the very same disease, very same parameters, very same initial condition. We are just applying a different contact matrix and a different population treatment. So this is just to tell you that when you start to introduce more realism into your model, you are able also to explain differences in the spread because contacts and population distribution changes across different settings. Okay, so these are the conclusions. So we have still 15 minutes, so maybe we can go to what we left behind. If there are no questions on this, we can go back to the boring part, but useful. Okay, so we have seen the mathematical objects. With pen and paper, we can derive they are 0. Okay, but if you want, I mean, we have seen these curves. You want to get those curves. How do you do it? Well, you need a simulation. So you need to write a computer program to do that. Big distinction between simulations. This is not specific to epidemic modeling. It's specific to computational science. We have deterministic simulation and stochastic simulation. So a deterministic simulation is something that if you run it 100 times, it gives you always the same results. Because it comes from a direct numerical integration of the system of differential equation, you will see what this means. What are the pros of this? It's easy to implement, it's very fast, and you only need one realization. Because you run it once, you have the result. You don't need to run it 100 times, because you will always get the same result. Stochastic simulation, instead, you already see it. You run it, you get a result, you run it again, you obtain a slightly different results. Because it takes into account the fact that these are stochastic phenomena. So, for example, the infection process. I can be in the same room with someone infected, I can get infected, but maybe no. I mean, this is a flip of a coin. These are more realistic. The point is that they are slower because you have to run multiple times. And this is an example. So here we have the, not sure if you can see it, we have a dashed line, and this is the deterministic simulation, and then the solid lines are the stochastic simulation. And you see that more or less they cluster around the deterministic simulation, but there is some variability. And then the nice things about the stochastic simulation is that you can compute statistics. So you don't have just one line, but you have you can quantify them certainly. So how do you implement in Python, but in any programming language, deterministic simulation? So there are books, entire books about how to integrate equations, system of equations. So what I will tell you here is the plain vanilla version of it. I think for most of the application in this regard, it's quite powerful. This is the Euler method. So the Euler method is relatively simple and says you have a derivative, you can discretize it like that. So you have the derivative of y in time. This can be approximated as the function evaluated in t plus certain delta t minus the function in t divided by the delta t, which is called the integration step. So what we do is that we apply this definition as it is to the system of the SIR model. So here we had ds in dt, and we write this thing, so on and so forth. Then you do a little bit of algebra, and you get an update rules. So you have that the number of susceptible at the next time step will be the number of susceptible at the previous time step minus these things that you can compute, because beta you know it, n you know it, I you know it, and you know everything. And this is again an update rule for the number of infected, and an update rule for the number of recovered. So from a programming point of view, you have a for loop basically. So you set the initial condition, you set the parameters, so mu is known, beta is known, n is known. You choose a delta t, which is generally 1, and you say, okay, s t plus delta t, I plug everything in and I solve this. It's very easy. And this is the implementation in Python, and this is on GitHub here. My account is NGOZZI. There is a repository with the code, but we can go through it very quickly. This is a function that implements the SIR model in a deterministic way. And you can see this is probably 12 lines of code. You initialize the compartments, you iterate over the length of the simulation, you compute the new number of infected, the new number of recovered, you update it, and you're done. And if you plot this, you get what we see. A possible problem of this approach is that the delta t, if you choose delta t which are too big, you may have some convergence issues, but this is a technical point I won't go into the stochastic simulation. I am not a fan. I mean, I prefer stochastic simulation. Here you don't have the system of equation, but what you do is that you actually simulate the process in general as a chain of binomial samples. What does this mean? Again, you initialize your system and you iterate through time steps. Okay? And at each time steps, you ask yourself, okay, what is the number of people that will transition from one compartment to another? And to do that, you sample that number from a probability distribution. Then you update the number of individuals in different compartments according to the transition, and you repeat. Let's go to the code that maybe it's more clear. Okay, so again, you initialize. So let's say at time t equal to 0, I assume to know what is the situation. And then you say, okay, let's compute the number of infected at this time step. And this will be a binomial sample. So this is a Python function that makes a binomial sample. This is a binomial sample. You flip a coin for a certain number of times. So for each susceptible has a certain probability of getting infected. So for each of them, you flip a coin, and this is basically binomial sample. So you say, okay, the new number of infected will be this binomial sample in which you have the number of susceptible, and this is the probability of getting infected. Beta times E divided by N. We have seen it. And then you do the same for the recovery process. You update the compartments, and you're done. In the previous slide, you have the pseudocode version of this. So maybe it's more clear. But as you can see, this is very few lines of code in which you simulate what you have seen in stochastic code. Okay, this was about simulation. The second part of the technical aspects in the last 5 minutes is model calibration. Yes.
Can I ask you something? So for this deterministic and stochastic simulation, does the initial state where you start from, does it matter? Because for the deterministic, as far as I can understand, you just run the code one time and it starts from one point. But for this stochastic one, you run it over and over and over again, so you have like different starting points, right? Or is the starting point just the same, or the convergence is the same?
I see the point. So in both cases, you start from a certain condition. So the initial conditions, you set them in the same way in the stochastic and in the deterministic. The point of a deterministic simulation is that if you run another simulation with the same initial conditions and the same parameter, you will get the very same results. In a stochastic simulation, you set the parameter, you set the initial condition. If you run this again with the same parameter and the same initial condition, you will get different results. I mean, not completely different, but you will see some changes. So initial conditions are very important, but the point is that if you change them in a deterministic, you will certainly get different outcomes. If you keep them constant in a stochastic simulation, you will get different results. What I say that you run over and over and over is that you run a simulation, you have one curve. Then you run another simulation, maybe starting from the same initial conditions, and you have another curve. You do this multiple times to have a statistics. So you don't have, okay, tomorrow there will be 100 infections. You will say tomorrow there will be median 100 infections with a confidence interval of 70 or 120. So you can have this. I hope this clarifies.
Thank you.
Okay.
The probabilistic distribution you choose is going to depend on what kind of data you have. You're choosing binomial here because it's similar to what the infection is like, but otherwise you could have any PDF, right?
Absolutely. So the choice of the probability distribution from which you are sampling will affect the results, but it's always grounded in the process. So for example, in the infection process, it makes sense, but in, for example, we modeled other transitions like assume you get a vaccine today, and you will have immunity maybe in a couple of weeks. It's not like a clock. In a couple of weeks you have immunity. You will have something which is around the 2 weeks, and in that case we didn't use that binomial sample. It didn't make sense. Well, we used the other distribution. In that case, it's called the Erlang distribution, which is used a lot to model this transition. But you're right. Okay, so model calibration. So this is something I really care about because I care a lot about implementation. So we have seen a lot of theory and some results, but I think that the implementation phase is as important as the theory phase. So we have seen how to simulate a model quite briefly. Another technical step which is very important is model calibration. So assume that you have real data, and your model has 3 parameters. So in our case, we have beta, mu, but the model can have a lot of 3 parameters. So how can you find the values of these parameters that reproduce the actual data? So this is called model calibration. Something we use a lot is approximate Bayesian computation. So this is a technique which has very nice features. And it is grounded into Bayesian statistics. Very briefly, Bayesian statistics is a branch of statistics which is opposed to the frequentist approach, which is the approach of the physicist, of the empirical science, let's say. And it is based on the bias theorem. And this is the bias theorem, and for you to know, and it basically says that the probability distribution of parameters given to the data is equal to your prior belief times what the data tells you. So the big change of Bayesian statistics is that it is two. The first one is that the importance of the prior belief. So in the frequentist approach, you are completely ignorant about the world, and you just make a measurement, and you get a statistic. In Bayesian statistic, you say, oh, you know what, I know something. I know more or less what the distribution will have to look like, but I also want to listen to the data. And the second most important piece of Bayesian statistics is that parameters are random variables. So in the frequentist approach, you assume that parameters will have some uncertainty associated, but because the instrument you use has some limitations. Here you are saying, no, look, the parameters don't have an exact values, but they are distributions. And this is very nice, especially when you want to deal with the stochastics phenomena like epidemics, because you basically are encoding stochasticity and uncertainty in a principled way in your models. Point is that why we need approximate Bayesian computation, because computing the likelihood function, which is this guy here, it's impossible. So what you do is that you need some empirical way of doing that. Let's try to, I want to give you an idea of what we are talking about. I mean, I'm sure this is quite confusing, so let's try to go to the action part. So now assume that you have a model, okay, the SIR model, and you have some pre-parameters, beta and mu. Okay. And you want to get the posterior distribution of these parameters. What is the posterior distribution of this parameter? Is the posterior is the probability distribution of the two parameters. So you are not assuming that beta is 0.2 and mu will be 0.1, but you will get that they are a normal distribution, something that looks like a normal distribution around certain values. Okay? How do you do that? Through this example, through this algorithm, for example. So this is called the rejection algorithm, and it's extremely simple and works like that. So you have your model, you have your parameters, you assume priors. Priors is, okay, you have beta, for example, and you assume that beta will be between two certain numbers. How do you choose these numbers? Well, for example, you look at the literature and you look at what makes sense. No? For example, R0. Assuming an R0 of 100 doesn't make sense. An R0 of 4, maybe it's reasonable. So you assume you choose the boundaries of the parameter based on reasonable values. Then what you do is that you sample from the prior distribution that you choose a parameter set. You generate the model and you produce an output quantity, which can be the number of infections simulated. And you compare the number of infections simulated to the real number of infections, the data. And you compute, for example, the root mean square error, some metric that tells you how the model is close to the data. And then you apply this rejection rule. If this thing here, which is, for example, the root mean square error, is smaller than a threshold, then I retain the parameter set. Otherwise, I reject it. And you repeat this iteratively. So at the end of this, the distribution of the parameters that you have accepted is an empirical approximation of the posterior distribution of the parameters. This is a practical example. We have the SIR model and we have real data, which are the dots. And we want to reproduce the dots with our model. And our only free parameters is beta. So you say, let's assume that beta has a prior distribution, which is a uniform distribution, between 0.01 and 0.06. So a uniform prior means that beta is some values between 0.01 and 0.6. Then we set some distance metric, it can be the root mean square error. And we say every time we sample a beta that leads to a root mean square error, which is smaller than 0.25, we accept that set. And we repeat this for 100 times, for 10,000 times. And this is what we get. So this is the empirical posterior distribution of the accepted beta. And you see that this is something which is around 0.3, which is the actual number I used to generate the trajectory. So this is good. And then, as a side product of this process, we also have all the trajectories that we have accepted, and we can compute the confidence intervals, the median, and so on and so forth. So this is a very powerful approach in which with a very stupid, allow me the word, algorithm, to get posterior distribution for the parameters and also ensemble trajectories. is the code. Literally this. What I do is that, okay, for the number of, for a certain number of time, let's sample beta from the prior distribution, which is a uniform prior between 0.01 and 0.6. Let's generate an instance of the model using the data that I've just sampled. Then I apply the rejection rule. Here, instead of using the root mean square error, I'm using another metric, which is the weighted mean absolute percentage error. And if this is smaller than the threshold, then I accept it. And that's it. Of course, this is a...
How do you pick the threshold?
How do you pick the threshold? So this is okay. So many times it's not. I mean, how the good part, the weighted mean absolute percentage error adds some interpretation. So you can say that your model is accurate at 20%. So what you can do is that, okay, I want a model that is accurate at 20, 30%. So what you do is that you pick something reasonable to do. But it can be a problem because sometimes you don't know, maybe your model is just not right. So you will never accept any parameter because maybe your model can't fit the data. So this is a extension of the algorithm that we have just seen, which is called ABCSMC, which SMC stands for sequential non-total. And this is a smart implementation of the rejection algorithm. And it works like that. So you start from a threshold which is very high. So you say, I don't know, I want a model that is 80% accurate, so something very bad. And you start with the threshold, you run the model, and you will accept a lot of parameters because you are putting the bar very high. Then you stop, and you reduce a little bit the threshold, you repeat, but the prior of the next generation will be the parameters that you accepted in the previous step. So you are basically starting from a very big parameter space and a very high bar. You start exploring all the parameter space, you will accept some parameters, and you concentrate on those parameters, you lower the bar, you want your model to be more accurate. Then you basically are cutting down regions of the parameter space which are not of interest. And there is also an implementation on the GitHub of this, which is a little bit longer. And by the way, I use a Python library that does all things, which is called PyRBC, and implement this thing.
The optimal threshold is when you cannot converge anymore.
Say the rest,
The optimal threshold is when you cannot converge anymore.
When the algorithm stops, you're saying. Here, there are many stopping conditions. For example, you can give a time budget. I want this to run 24 hours. Or I want this to run up to a certain, I mean, if you reach total number of simulation, I want this to stop. Or then you set some, if the threshold has reached a certain level, I want the algorithm to stop. So there is a trade-off between how much computational power you have and how good you want your model to be. I have designed it.
The threshold is so low that you might not be able to fit the data.
Okay, yeah. This is the good. I mean, if you set a very small threshold, your model will never converge. So this thing, yeah. But if you implement this, you don't have to specify a small threshold. You put a very high threshold,
And then you lower it down.
and it lowers down automatically, and it will adjust.
But at some point, you won't be able to.
This is why you put the stopping condition. So you say, okay, if this runs for 24 hours or for 10 generations, you repeat this 10 times. So you put stopping condition. At some point, this will stop.
The success risk was zero, the length is zero issues.
Yeah, for example. And the point is
There's
that,
nothing else you can.
yeah, you put some stopping condition. Yeah, based on the total budget of simulation, total time, if you reached a level of satisfying level of performance. So yeah, this thing.